In this section, we will talk about running Julia in batch mode. We will see what is a batch job and how to make a batch job. And also we will provide you with a short introduction to Slurm scheduler and show you the structure of a batch script. So we have some projects for Rakan, Kebnekaise, and Cosmos that you can use during this workshop. And we have also prepared some storage space, yes, on Rakam and Kebnekaise. As you can see here, this is the path that you can use to put your folders, yes, for this course. And on Cosmos, you can choose your more convenient place to put the folders, yes. So this is important, especially in HPC. Yes. Any longer resource-intensive or parallel jobs must be run through a batch script. So the batch system that is used at LUNARC, UPPMAX, and HPC2N is called Slurm. And Slurm is a job scheduler that provides some functions. For instance, it keeps track of available resources, hardware resources, and also enforces the system resource usage and job scheduling policies, right? And also it manages the job queue. So to submit a job to this Slurm queue, you need to prepare a file, right, which is called a batch job or batch script or job script. And there is a more detailed documentation on our websites for each center, right, that you can find here. And essentially, when you work with batch jobs, you need first to write a batch script, which is a text file. And inside this script, you need to put the modules, load the modules that you need. In the present case for this course, you will need the Julia module. You will need also to activate the environments in case you have that for your project and ask for the resources that you will need in terms of course, in terms of tasks, in terms of memory, and then you need to pass the inputs to your Julia script. And finally, once you have the script, that in this case is called my Julia script.sh, right? So then you submit the job to the queue by using the sbatch command. So you can use some endings for the files. In this case, I use sh to denote the batch script, but you can use whatever you like. You can use, for instance, .batch. So it's not important, but it's also convenient and also to be consistent with your nomenclature so that you know that this is a batch script. So you can use or some ending for all your batch scripts so that you know that this is a batch script. So there are some useful commands to deal with the batch script to control or to monitor the jobs in the queue and also to get information about your jobs that are in the queue. And here there are some of the most useful commands, right? Here is the batch script command, yes, to submit the job, right? And here, if you type this SQ minus U and your username, then you will get all the queues, all the jobs that are in the queue under your username. So if you want to get more information about the job that is on the queue, you can type S control show job and the job ID. Job ID is the number that you get when you use the batch S batch command. Yeah? So if you think that you don't need this job any longer, or there is some issue, or you just want to cancel that, then you can type S cancel and the job ID. More useful information can be obtained with this command, which provides you with more details, right? And you can use this as a pipe, yes, to get the information in a in a in a buffer or in a window format. So this, I like this command. This it called job usage at HPC2N. It's also supported at other some other centers in Sweden. And here you type job usage, job dash usage, and the job ID. And this is command is available on the Kebnekaise terminal. And then you will get a URL that you can copy and then open a browser in your local machine. For instance, here sitting on Windows, I can open a browser and paste that URL, and then you will see the statistics of your job regarding the CPU, GPU, and memory usage. So here we provide you with some examples for the codes in Julia. This is for a serial job. As you can see here in this tab, this will print some a string. In this case, is hello world. It's very simple. And then there are some scripts for submitting this job to the queue. Essentially, what you can do in this type of format in a web page is that you can go and copy these commands here. Then you go to your folder where you are working in the corresponding machine, and then you can create a file by using your preferred editor. In this case, this is my editor, and I just pasted the commands that I have here. So the script is already there. Then I go to my script here that this is available. I copy that. Then I can open or another file. I will call it, for instance, job serial.sh. And here I need to write the project name. So in this case, because this is a serial job, I will write just one core. The time is 3 seconds, and the rest is this similar. Then I need to write the name of the script. As you can see here, I have several scripts, but this is the one that I need, right? Julia is the name of the executable, and then the name of the script serial.jl. So then I submit this job to the queue. And if I type, for instance, SQ minus U and my username, I will see that the job is not there because most likely it ran already. So let me see. So yes, the output is already here. So, but if the job takes longer, then you can see the displays on the queue, and this is the job ID that you will use in for the other commands. So then I can open the output file, and you will see that it printed out hello world. So this is the way to submit a serial job. And we also cover in the previous section the virtual environments. So in case you have some virtual environment, yeah, you can run this exercise. So this command can be copied and pasted in your environment. If you remember in the previous example, I created an environment called my first M. So I will open this one. And inside this folder, I will create a file called serial dash env.jl, and I will paste this content here, which will list the status of the environment regarding the installed packages. So now this file is inside the folder where I initialize the environment. So then for Kebnekaise, I can copy this bash script. Then I can create a file here called a job environment, for instance, .sh. And then I will paste this information here. Here I have the project ID, the name of the job, and also the time that will take. And notice here the main difference is that here I will activate the project environment with this dot, which means take the environment in the present or in the current folder. So then I can submit this job. I can take a look at the queue, and you can see that this is the job ID. It started running, and it ran quickly. So then I can take a look at the output file. This is this one. And here you can see that the status of the project shows that the DFTK package was added as we did it in the previous section. So this is how essentially it works if you have an environment, and it's very convenient to work with environments in Julia because they will isolate completely your project. So regarding parallel code, there are different types of programming models that you can apply here. And specifically, we can see that there are two very interesting and useful packages that are included in the base installation. So in the standard library of Julia, so you don't need to install them, right? So this is very convenient. They are part of the Julia base library. So, but if you want to use something else like MPI, message passage interface, then you will need to install this additional package. So, and this is more advanced as well, and you can follow these steps here to get MPI running. Especially, you need to pay attention to setting the correct path. So this flag here will set the path to the MPI wrapper, right? That will allow you to run an MPI code with Julia. So here I presented you with some examples, right, on how to deal with a serial code. We saw previously how to run a serial code that printed out the hello world string. And this is more elaborated. This is a two-dimensional integration, right, of some function. In particular, this is the sinus function between 0 and pi, right? So what you do here is, or this basic or naive implementation of an integration, right, employs two for loops, and one is for in the x direction, and the other is in the y direction to cover the square between 0 and pi for both directions, right? And then you collect the summation in this variable my sum. And finally, when you get this accumulated value, you multiply it by the dimension of the grid, is it the grid piece, the grid bin, right? The grid bin. And once you have this, you return this value, and this will be the result, which is printed out here in this place. So notice here, this is a naive implementation of Julia for the two-dimensional integration using two for loops. The for loops in Julia are very efficient. They are not like in Python or R. Yes, they are very efficient in Julia, so you're not penalized for using these loops and or even the nested loops. It should be quite efficient, right? So now let me go to the threaded program, right? So immediately you see that there is a difference in the programming style, right? So first of all, we need to define the number of threads here in this variable, and then uh, we need to set some array for storage, storing the partial sum from all the threads. And this will allow us to compute the summations for each individual thread, right? Thread is one specific task that will allow us to compute part of the total workload. So here we create a function called Julia integration to the Julia threaded, which accept the size of the grid, the number of threads, and also a thread index. So this is the size of the grid for both directions, x and y. This is a cumulative variable. And here start the part that we need to implement to make the program aware of the different threads. Here we define the workload, yes, which is the total grid size divided by the number of threads. So each thread will get the same workload. Yeah? And here we need to define the lower limit and the upper limit for the parts of the array that the thread will compute depending on the thread index. For instance, if the thread index is the thread 1, it will start from thread 1 minus 1, 0. So this will start from 0 and then finish at the the value workload. Yeah? And here we start the integration. Notice here that this function is not computing the entire range, but just one part from lower limit to upper limit. And finally, here we accumulated the partial summation for each thread and run the function which this decorator, yes, that is add threads. This add is not a comment, is an instruction from Julia to reflect the number of threads. And this is included in the threads package. So here we start the integration from the whole range of threads, right? And then we compute this summation. And once this summation is computed, the partial values are stored in this array. And then you just compute the summation to get the total integral. So you can see here, I changed my paradigm from integrating over the whole range to just compute part of this range for each thread. So this is for the threaded mechanism. So we have also the distributed mechanism that is offered in the distributed package. Yeah. So in this case, we have something similar as in the previous case, the grid size, the number of workers. In this case, we are not talking about threads, but the terminology is the workers or processes. So we also define a partial array or a shared array to collect the summation from each worker. Then we create another function called integration Julia distributed, which accepts similar parameters as before. We also need to define the workload for each thread and then iterate over the limits allowed for each thread. So then we collect the partial summations on the shared array. And finally, we execute the whole loop by using the distributed decorator, yes, that is defined in the distributed package here. And finally, we collect the partial summations to get the total integral. So you see here that the pattern is repeated in both the threaded and the distributed mechanism. And in the case of the MPI, the situation is similar, except for the fact that we need to initialize some MPI variables, yes, as I'm doing here. So we initialize this, and then we are able to use the different processes. And here we do something similar as in the previous cases, collect the partial integrals, and finally, we use a reduce operation to get the total value. So these are some examples, yes, to perform a task of integration. You can get the idea from this to apply to your code. And here there are some examples on how to run this code, yes, in your machine, UPPMAX, HPC2N, or LUNARC. Yeah. So for the threaded case, we have seen this serial job. I can show you here for the threaded case. This is the script. And in this case, we will be using 8 cores or 8 tasks. Yeah. So I can copy first example for the threaded case. And I can open a file called threaded, which is already there. No, it's a different one, sorry. I pasted the content, is the same. And then I use the corresponding batch file, which I will call job dash credit.sh. So you can see here, I will use 8 tasks. And here, this command is not obligatory, compulsory. This is just a command that I use to monitor the time that it takes. Yeah. So once we have this, we can launch the job. Then we can take a look at the queue to see if it is running. So it is running. And we can monitor the output files. This should be here when it finishes. So and you can see here that the integral value is this one. So the exact value is 0, so that it is close to this number here. Is 0.32 minus 11. So we are getting the correct value, and here you can play around with the number of cores or tasks to see how fast or how slow your simulation run. So this is an example for running a job in GPUs. And here there are some uh, requirements that you need to fulfill to use the Julia with the GPUs. So in particular at UPPMAX, you can open an interactive session as you are seeing here with your project ID, then load Julia and start Julia, and after that, you can add the package CUDA. So at HPC2N, you just load the Julia module, which I did already. Then we will load the CUDA module. In particular, this is 11.4.1. It should be there now. Then I start a Julia session. Then I move to the package directory or the package mode, sorry, and then I add the CUDA library. So this is something that you need to do before using the GPUs with Julia. It takes some time, but because I did it, I added previously CUDA, so it is only updating the TOML files that I mentioned previously. So it doesn't need to install and download things again, even though it takes some time, as you can see here. So now we are ready to use the GPUs. We have some test case here. So this is some computation that we can do. So notice here that we are using the CUDA package that we just added. Here we will print out some information of the available hardware, yes. And here we start some computations. These arrays are defined on the CPU side, yes. Then this is how you define two arrays on the CPU side. But if you want to use these arrays on the GPUs, you just need to write Q array and the name of the array, and this array will be now stored on the GPUs. Yeah. So now, if we want to perform a calculation with arrays on the CPU, so we just do x times y, for instance, to compute the multiplication. But if you want to do this operation on the GPU, we type A times B for these two arrays. Yeah. And we can do other operation as well. It's convenient to, here I am repeating the information, the calculation, as you can see, because I want to show you that the first time that you do this calculation, the data, this part, the data will be moved to the GPU, and because of that, it will take some time or longer time to run on the GPUs. But the next time that you do this computation, because these two arrays are on the GPU side, then it should take lower or shorter time. So then I can copy this example here, and I can create a script. So in the case of the HPC2N, I just copied this script that I can call job gpu.sh, for instance. I paste the content here. And the script, notice here that besides Julia, I need to load the CUDA module that I used during the settings. Then to execute the script, I type Julia script dash GPU and .jl. Here I choose the type of node that I want to use, and I can choose, for instance, between several options. Yeah, and here there is one a V100, but at the moment the L40s are less busy, I would say. And because of that, I will use, instead of V100, the L40. Yeah. So let's see how it goes. I can check the queue, and you can see that it is running. I can take a look at the jobs. And here you can see the output when the job finishes. So here there is the information that was printed out for this CUDA version, right? It prints out the information of the drivers and the libraries that are used, and also the device, the hardware. And here you can see the timings, yeah? So here you see the time, let me see. You see the different timings. Here you can see the time for the CPU, and then you can get the times for the others. Let's wait a little bit. Well, what happened? Okay, let me check. Okay, so it seems that only one is computed. Interesting. Let me see if we go to the errors, you will see, okay. Okay, the timing that was printed out was for the CPU, and the GPU was not computed at all. So it seems that there is some issue with the library, yes. And my guess is that it is due to the CUDA library that is available on the L40 nodes. So I need to update this CUDA module here. So let me see how much time I have. Okay, so I will try one more time. I will take a look at the CUDA versions that we have installed, and I hope with this one I am loaded Julia, then loading my CUDA, my module, open the Julia session, and then I will add CUDA with this CUDA version that is here. So this should work with the V100 card, yes, but because I changed the GPU, because they are less busy at this point, one needs to choose the proper CUDA version. So I will exit this thing here, open my job usage. So instead of this one, I choose this one. Let me try. Then I submit the job. And let's see. Now you can see that here the problem was the module for the CUDA version on the L40 GPUs. So this should work on the V100 as I mentioned. And here you have the timings for the different runs. You can see here the first time that you execute the multiplication on the CPU side, yes, and then on the GPUs, it takes you see it takes longer to execute than the CPUs, and you can think that it is not worth it to use the GPUs. But this was because you needed to transfer the data from the CPU to the GPUs. But the second time you execute it, you see that because the data is already there, you only need to perform the computation. You don't need to do the allocations. Yeah? So this is quite convenient. And you can use the GPUs just by using these Q arrays instead of the normal arrays, right? So slight modifications on your code. Of course, for more specific computations, you will need most likely to invest more time in your coding. So Julia provides you with some cluster manager, right? And the idea is that you can start a cluster and then perform the job in a more interactive manner. For instance, here you add some processes to some scheduler. In this case, is learn. In this case, I'm just adding two processes, and then you can start doing some computation, right? As in this case, you are computing the square root on the number of processes that are requested. So this will allow you to do more interactive jobs. Instead of sending the jobs to the queue, then you can start some jobs here and some parallel task, and they will be executed as if they were on the queue. And when you finish with this cluster, then your parallel task will be terminated. So here you terminate the cluster just by removing the workers. So this is more interactive and it's also a nice feature. Here there are some exercises that you can try for this session. You need to run a serial script and also a GPU script similar to what I did previously. Yeah, I can stop here, Bjorn.